In the last video, we looked at the basic principle of operation. In this video, I want to focus on how we can address the fundamental limits of efficiency of this motor. So if you recall, this is the motor that we're studying. We have an angular displacement, theta sub m, which is would be 0 for this coil position. So it's pointing to the right, and as we rotate counterclockwise, that would be a positive theta. The angular rate, d theta m dt, is omega m, the angular, the rotational speed of the motor or the coil. In this video, we're going to consider the case where we're going to apply a fixed coil voltage. V coil is the external voltage applied right across these rings here. And we are not going to be directly controlling the current. The current will be a response to applying a voltage across here, as well as a function of how quickly the motor is already spinning, because as we saw last time, when the motor spins, there's an induced voltage. Faraday's law of induction describes how a voltage will be induced in this coil, and that will offset the voltage that we're applying at the coil external terminals here. The difference of those two voltages being the voltage that is applied across any coil resistance, and that's how we determine what current flows through the coil. The physical system we're studying is a small one. This is because we're motivated by this horizontal Mendocino pulse motor, and it's a low power unit. Okay, so B naught, the DC field, magnetic field, is around 72 Gauss. There's 500 turns of coil. The coil resistance is about 30 ohms. The length of the coil is 0.8 inches. Okay, so we're going to go to some of the results now and focus on how we can improve the power efficiency. So what we had noted last time, and what I'll hit on again here briefly, is in this plot we see the input electrical power, PE in, and we see the mechanical output power, PM out, here in blue, and these are a function of theta m, the position of the coil, the rotor coil. And this is normalized to pi, so we're talking about minus 180 to plus 180. And we're assuming right now that we're powering the coil with 1 volt, and the motor is spinning at a rate of omega m equal to 80 times 2 pi radians per second. And we are studying it over 1 full revolution. And what we note here is that the output power, the amount of power that is delivered to the mechanical side of the motor to overcome any friction, accelerate it by delivering more energy to be stored in the rotational inertia, or to be delivered to some mechanical load that's connected to the output of the motor shaft. That is going to be supplied by the orange dotted line here. And we see that it is broad and flat fairly over a pretty wide range, and it drops to 0 when we get to minus 90 degrees or plus 90 degrees. And beyond that, the power is actually negative, meaning that the motor is now acting as a generator. So we're returning mechanical energy back to electrical energy, which is not what we want to do in this case. The blue line shows us the input electrical power, and we note that it is closest, but always greater, to the output mechanical power right here at the angle of 0. And as we move further away and toward plus 90 or minus 90 degrees, we see that it rises further and further until at plus 90 and minus 90 we have no mechanical power going out, but yet we have so far a maximum electrical power going in. And the distance between these two is the amount of power that is being dissipated in the coil resistance. So energizing the coil out here at the skirts is an inefficient process. We deliver a lot of power to the coil resistance, but increasingly small amount of power actually is delivered to the mechanical system. So because of that, when we look at the efficiencies of the motor, now we're looking at the power efficiency over a whole cycle. So we're running the motor over a full cycle, and we are going to have we're assuming the coil is conducting for a conduction angle of pi. You see pi right here as an argument. Now pi, what it means is that we are conducting from -90 to +90. It is centered about 0. So we're going to conduct over the full maximum range for which we can deliver power. Even though it's reduced, it's vanishing here at the edges. We're going to energize the coil over the full -90 to +90 as our starting point. And when we do that, we see that there's a maximum efficiency that occurs as we sweep the external coil voltage. So here's 1 volt up at the end here. But as we bring that voltage down, we find that there is a voltage around 0.84 or so, where the efficiency is maximum for the case where we're spinning at 80 times 2 pi radians per second. The orange line is where the angular frequency has been reduced to 80%, so 64 times 2 pi, and then this would be 48 times 2 pi. And we see that the efficiency maximum point occurs at a lower coil voltage, but it never exceeds this limit, which looks somewhere close to 40%. And we saw last time that actually the maximum efficiency is 39.38%, and that's a theoretical maximum efficiency that we cannot exceed so long as we energize our coil for a full 180 degrees, in other words, -90 to +90. In this plot here, we're looking at how that efficiency changes as a function of angular frequency for a fixed voltage, 1 volt, and then we have a second curve here where we're powering at 0.8 volts. Okay, but in either case, the curves, though they're different, they both max out at that 39.3, and so we can't get above that efficiency. This is interesting curve in that if you imagine the motor starting up from rest, as it moves to a faster and faster speed, its efficiency actually goes up until it reaches some maximum efficiency. And we might ask, well, do we stop at there and operate at the maximum efficiency, or do we go beyond the maximum efficiency? And this is all going to depend on how much output power is going out at a function as a function of the angular frequency, and then what is the loss as a function of angular frequency, and those have to meet up. So no, we will not necessarily operate at the maximum efficiency. We might operate below it, we may operate above it. It depends on the lossiness of the system that we are connected to. Okay, so now we're going to go into the real content for this this video, which is to consider how we can increase the efficiency, this underlying 39.3% efficiency that we saw. Okay, well, what we're looking at here is we are sweeping what we're calling the conduction angle. So the conduction angle is the angle over which the coil is energized, and up until this point our conduction angle has been fixed at pi, basically from -90 to +90. That corresponds to the point out here at 1, which is basically pi. We're going minus pi to plus pi. The middle point here at 0.5, or half a pi, we're saying that we're going to have the coil energized for theta m from minus pi over 4 to plus pi over 4, rather than minus pi over 2 to plus pi over 2. And when we get down here to, to a very small conduction angle, we are essentially just energizing the coil over a very narrow region right here, right about 0. Okay, so a little bit to the left, a little bit to the right. And of course, as we make that conduction angle smaller and smaller, what we see is that we're operating the motor where the efficiency is greatest. Notice that the input power is closest to the output power here, so there's not a lot that's being lost. However, because we conduct for only a small portion of the full 2 pi cycle, we're not able to deliver much average power, and that's what we see from this curve here. So the orange curve on the which corresponds to the right side here is the average output power, and we're plotting it for a coil voltage of 1 and a coil voltage of 0.8, and we see that it's maximum when we do have a conduction angle that's over the maximum, basically the maximum conduction angle of pi, and it decreases as we go down in conduction angle. But the blue on the left axis here, representing the efficiency, the power efficiency, we see that the efficiency keeps going up as we go down to smaller conduction angle. So a good design, or one that would be able to capitalize on higher efficiency, would be one where the motor was designed to be able to output a maximum output power when the conduction angle was pi that was significantly higher than what the mechanical system would require. So it's such that we can operate the motor down perhaps here at half the maximum output power. So let's say that the mechanical system that we are driving only requires 2 milliwatts. Then we can operate the motor right here at about 0.5 pi, and the motor can put out the 2 milliwatts, and our achieved efficiency is around 65 to 70% efficiency, which is much greater than the 39% efficiency. Now I should note that in a normal DC motor that has commutation brushes, there are multiple coils on the rotor, and so each coil is offset by so many degrees. So if there are 3 coils, they would be offset by let's say 120 degrees. If there's 8 coils, or let's say 3 coils, 120, 6 coils, 60 degrees. And so in those cases, we can get away with only energizing a single coil for a fraction of the full 180 degrees, and thereby operating that coil only at its maximum or around its maximum efficiency point. But before we have moved too far away in angular position from where that coil operates with maximum efficiency, we disconnect it and we connect the next coil, the next phase, as it approaches being at its optimum efficiency point. And when we put a number of those together over a full rotational cycle of the rotor, we can increase dramatically the net efficiency, power efficiency of the motor. In a single phase coil motor, we don't have that opportunity. We have to trade off power for greater efficiency as we decrease the conduction angle. So that's what we have to live with. Okay, so let's see, what else do I have here? Oh yes, what was the difference between here and here? I think, are they the same? Power efficiency and average output power versus conduction angle. I think this is actually the same slide. I forgot. Power efficiency and average output power versus conduction angle. Yes. Okay. Well, that's a repeat. Okay. The last thing I want to do is to show you this slide here, which is an attempt to consider what happens if instead of changing the conduction angle, we actually offset it from the center angle of 0. Let me go back to this slide right here. So far we've looked at increasing the conduction angle by symmetrically increasing it on the left and to the right. So let's say we have a conduction angle of pi. So it would start at minus 0.5 and it would conduct all the way over to plus 0.5, and it's centered at 0. So this would have an offset angle of 0. But let's say I gave it an offset angle of 10 degrees. Then this 180 degree pulse would now move to the right by 10 degrees and be offset. It would go from minus 170 to plus 190. Okay, clearly this is not a good thing. This is not going to be as good as if it's symmetric about 0 with an offset of 0. However, in reality, when we design particularly an analog circuit, it's going to be difficult to make this exactly symmetric. So the question is, can we predict how badly we move off of our optimum efficiency or optimum power output point? So that's what this last slide is doing, and I can show you maybe first how I modified the equation right here. Okay, so here's my electrical input power and mechanical output power, and we're simply taking the work and basically dividing it by the period, which is the multiplying by omega m over 2 pi. But these two angles are the start angle and the end angle, where I'm going to integrate from some starting angle. Let's see here. Yeah, so if I start from minus 0.5 and I integrate to plus 0.5, this would be my start angle, this would be my ending angle. And what I've done in this definition here is to take the conduction angle, divide it by 2, so this becomes my start angle here, this is my end angle, but then I've shifted both of them with the same polarity by a theta offset. So we add theta offset to both of them, so I can shift it to the right or shift it to the left, and I've done the same thing for PM out. Okay, and what we see is this response right here. Okay, so let's look at, I have two different curves because I'm looking at a fixed conduction angle of pi. That's our maximum angle that we can energize the coil over before onset of actually having a net negative power delivered, right? We start using the motor somewhat as a generator. So this is where we're maximizing the conduction at a fixed 180 degrees. And then the second case here, which is plotted with the dotted line, is where we are limiting our conduction to 90 degrees. Okay, so we're going from minus 45 to plus 45 degrees. That's what this center point is right here. So let's look at the full conduction case first. Here is our efficiency. We're at that 39.3% right there. That's the best we can do. And then as we move off of center angle for our conduction of 0, our efficiency drops either side, right? And I'm sorry, that's our yes, that's our efficiency right there. And our power, which is the orange here, also decreases. Okay. Now, do this right here. Now let's look at the case where we're only conducting for minus 45 to plus 45, or a total of 90. Okay. Now our efficiency first is going to be much higher. Our efficiency gets up to, it looks like 80%. And our output power is going to be lower, clearly lower. It looks like about 8 milliwatts as opposed to 18 milliwatts or so. So it's lower. However, as we move off center, notice that the power, the output power, does not suffer as quickly as it does for the case where we're at our maximum conduction angle of 180 degrees. So we actually can move to the left or to the right, and we can actually get a little bit more output power, but of course the efficiency drops as soon as we move away from it. But because we're starting at such a higher frequency, and because it decreases to 0 over almost twice the distance as what the efficiency curve covered for the case where we had a full conduction angle of pi, the slope here is going to be shallower than in this case. So the bottom line is there is less stringency on centering our pulse, our conduction pulse, if we're not conducting over the maximum range of pi, or minus 90 to plus 90. We have some wiggle room, right? Because if we're only going from minus 45 to plus 45, we can theoretically move plus or minus 45 degrees before we actually move out of the motor range and start getting into the generator range, where we're returning energy back to our electrical source. So if you are looking at changing the motor driver, either for doing so by way of an analog circuit, discrete circuit, or because you're going to add digital control, maybe with the microcontroller, and you're going to be controlling the pulse width and the position of that pulse, in both cases, these results should prove useful to you.